Okay, so let's go over to the sample. And now you might think that, okay, but we already talked about the sample, so what's different here? But as I said earlier, since the laser is so organized both in frequency and spatially, we can actually enhance the absorption, and we can use different tricks to enhance the absorption. And they are all based on the following fact, that we have some light intensity coming in, and it goes through the sample, and then we have some light intensity coming out. And we want the absorption to be large, so that there's a large difference between the input and the output absorption. That means that's just saying that this dip is big. Now this dip is governed by something called, the absorption is governed by something called Beer-Lambert's law. So that basically seems that the light intensity afterwards here equals the light intensity we send in times e to the power of minus alpha, which is the absorption coefficient, times the length. So we can either choose something which has a higher absorption, and that's, for example, what we do when we do mid-infrared spectroscopy, where the absorptions are very strong. But the other trick is to make the path length very long. And sometimes we can make the apparent path length very long. That means that we want the light to pass through the sample very, very many times. So we have already talked about optical cavities when we talked about Fabry-Perot cavities earlier on. But let's look a little bit more in detail on optical cavities and give a different description of why they are useful for making the path length long. So we have some light coming from this side, and when it comes over here, here is a mirror, so it hits the mirror. Now these mirrors can have very, very high reflectivity, like in the range of 99.999%. That means that almost all light, if it has this high reflectivity, is reflected, and only a very, very small part leaks into the cavity. Okay, but if most of it is reflected, but the light then goes over, it bounces on this mirror over here, and if we are resonant with the cavity, it bounces on this mirror, but if this mirror is also highly reflecting, like 99.999%, I mean, even if it both are 99%, this still happens. But almost all of the light is reflected back, and then it's reflected from this mirror again. And if we are on resonant with the cavity, what that means is that the light which now leaks in, it has the same phase as the light reflected from this mirror. And then all of this light, so now we have twice as much light, and all of this light goes over here, and then it's reflected again, and again we have leakage, and the light inside the cavity which has been reflected has the same phase. So we can sort of see it as the light inside here is trapped. And let's, for example, say both of our mirrors are 99% reflecting, and we have no other losses. Then this process will keep on going until we have 100 times more light inside the cavity than the light coming in. And at that point, so that means we build up a intensity inside, and now it's not very representative, because this intensity can be much, much, much higher than the input intensity. And also, since our light is bouncing forward and back, forward and back, forward and back, if we have something absorbing inside this cavity, the light passes it very many times. In the example, if we have 99% reflectivity, it on average passes 100 times. But if we have 99.999%, then it will pass through the sample inside here 100,000 times. So if this cavity, for example, is 10 centimeters long, that would correspond to a cavity which was 10,000 meters long, or an interaction length, sorry, not a cavity, an interaction length which is 10,000 meters long. But of course, now when we have much higher intensity inside, a little bit of a light leaks out. And if we have no losses, and we are perfectly on resonance with our cavity, and the reflectivity of these two mirrors are the same, and there's no scattering, anything like this, the leakage out here will be exactly as big as the input light from this side. Okay, but we had a large part of reflecting, so don't we have some problem with this, that we now have reflection here and we have transmission here, that this doesn't follow energy conservation. But what actually happens is we have leakage in this direction, and we also have leakage out. And we have much stronger intensity here inside than we outside. And the leakage out here when we are on resonance have an opposite phase when we're reflected. So the leakage from inside have the opposite phase, so these two light beams cancel each other. So that means on resonance, no losses, we have no reflection in total after we have built up intensity inside the cavity, and we have the 100% transmission through the cavity if there is nothing absorption. But if we add an absorption inside the cavity, we can see that on that we have less transmission. Okay, so this means that we can since we have so organized lights from our laser, we can enhance the interaction length by using a cavity. And this is used in several different very sensitive spectroscopy technology. Oh yeah, there's the transmission arrow as well. Okay, so how can we now use this to make very accurate spectroscopy? And here there's a lot of stuff on this slide, so we'll take it one thing at a time. So let's say we take a laser and we take a cavity, so that's this mirror over here and this mirror over here. And we'll make sure that the laser is resonant with the laser cavity. So that's just this red one here, and all of the blue ones here are the cavity mode. So we say that this red one here, we only care about this one now, it's resonant with this cavity mode. And then we scan the length of the cavity while at the same time making sure the laser is always resonant with the cavity. So we basically scan the length of the cavity, that means that these modes will move, and then we'll move the laser together with this. And when we now encounter an absorption, since it bounces forward and back so many times between these mirrors, that means that we will get a decreased transmission, increased absorption length, and we'll get a decreased transmission which is much larger than it would have been if the light only passed through the cavity once. Okay, but again there's a lot more things on this picture, and we'll go through them one by one. So over here is something called a phase modulator. And a phase modulator is a piece of crystal which has the property that when you apply an electric field over it, it changes its index of refraction. So you apply a electrode on this side of a crystal and one electrode on this side of a crystal, and then you send in a synovial electric signal and apply it to your electrodes, and thereby you get a varying electric field inside this crystal. Now, since the index of refraction varies, that means that the optical length of this varies, and if you look after it, that means that the frequency, instantaneous frequency of a light coming out will vary. So you see here the sinus wave is varying faster, and here it's a little bit stretched out, and so on. Now, if you do a frequency analysis of this signal here, it has the modulation which you apply here is not so large. It has the carrier, that's the original frequency, and it also has two sideband, one sideband here and one sideband here. And one of them is drawn negative because depending on how you see it, it has a different phase. Okay, and the separation between the carrier and the sideband is exactly the frequency of electric signal which you sent into your electro-optic modulator. But notice also that the frequency or the phase changes with this signal as it comes out here, but the intensity is the same all the time. So that means that if we were to put a detector here, we would not detect any intensity modulation. And this signal here can actually be used immediately for spectroscopy without the cavity. So let's first look at that kind of spectroscopy, and then we'll go back to this picture again and combine them. So in this kind of spectroscopy, we have another picture here. Again, we have a carrier here, we have the two sidebands from our previous pictures, and now we have some absorption profile here. So we can tune the laser before the modulator, which means that we can tune so that we move this, and we move one sideband into this absorption. And if one sideband moves into the absorption, that means that this sideband will be partially absorbed after we have passed our signal. And remember, there was no intensity variation originally, but if one of these sidebands goes missing, then you will get an intensity. Then this symmetry will be broken, and you will get an intensity variation. And this intensity variation is on the frequency of the modulation frequency. So by measuring on the modulation frequency and see if there's an intensity variation, you can detect this absorption. And this is very favorable because lasers has something called 1/f noise, and this means that there are slow fluctuations out of a laser in the intensity out of the lasers, and these are typically up to about a few kilohertz, up to 10 kilohertz or so. You have this 1/f noise, and that means that if you are trying to measure absorption at low frequencies, you are at the same time is measuring this 1/f noise. But now you have your absorption at the frequency of your modulation, which you can choose freely. So you can choose 50 megahertz, which is way, for example, 50 megahertz, which is way above this 1/f noise. And that means that you can make very detection for very accurate detection. Okay, let's now move back to the previous picture. Oh yeah, so here is a picture where you do this modulation spectroscopy. Here is the absorption signal at baseband. That's what we call it if we just scan the laser and measure the absorption at low frequencies. And here is the same absorption if you are doing modulation spectroscopy. So you can have a much lower noise from your signal because your laser you get rid of this laser noise, this variation, this sort of variation in intensity, which you can see on this picture. Okay, so let's now combine this cavity spectroscopy with this modulation spectroscopy. And to do that, we have to get the sidebands into the cavity. So then we match the modulation frequency with a free spectral range of a cavity. That's just saying that this sideband here is placed inside the next cavity mode, and this sideband is placed inside the next cavity mode. And then we scan the laser, and then the side modes, of course, the sideband scans with it at the same time as we change the length of the cavity. So we scan the whole thing together. And now when one of these sideband, since this is also resonant with the cavity, this is also bouncing and forward and back many times, enhancing the interaction with absorption molecules. So if we look at the output here, we will have exactly the same thing, that we will have a modulation. If this is absorbed, we will have a modulation on the modulation frequency. We'll have intensity modulation on the modulation frequency, phase modulation we had before, but it will be enhanced by the cavity. And this whole setup can be made very sensitive, and this is called noise immune cavity enhanced optical heterodyne molecule spectroscopy, or NICE-OMS for short. So let us now move on to another cavity enhanced way of measuring absorption, which is measuring small amount of absorption, which is very different. So this next spectroscopy, cavity enhanced spectroscopy method, is called cavity ring down spectroscopy. And I will explain, this can use both pulsed lasers, but I will explain the one using a continuous wave laser. Okay, so we have a laser over here, and in this case we have a ring cavity, so that means that we have a mirror here, we have a mirror here, and we have a mirror here. And the laser light inside the cavity bounces around like you see here, round like this. Okay, so when we turn on the laser, it will hit the first mirror here, and since it's a highly reflecting mirror, most of it will be reflected down in this direction. But a little part will leak into the cavity. It will be bouncing around like this. And if we're on resonance with the cavity, that means that we slowly build up intensity inside the cavity. That's what we see here. And as we slowly are building up this intensity, we will have some leakage with opposite phase from the reflection leaking out here. And after this is fully built up, there will be no reflection from this first mirror here. And we will have high intensity inside the cavity. If we now at this point, so we're up here in our diagram with a high intensity inside the cavity. Now we just turn off the laser. So we turn off the laser, but we still have intensity inside the cavity. And we have a detector over here detecting the the part of the intensity which leaks out, remember it's bouncing around, so some of it leaks out in this direction. And since there are losses every time the light hits when the light hits the mirror, some of it leaks out, for example, towards the detector here. That means that we will have a decay of the intensity coming out. We will have a decay of the intensity inside the cavity. And this is called a ring down. Okay, but if we now have some molecules inside this cell here, that means that we will increase the losses. And if we increase the losses, that means that our ring down time will be slower. So we build up our intensity, and then we turn off the light, and without a sample we have a long ring down time, but with an absorbing sample we have a shorter ring down time. And we can then fit an exponential decay to these curves, and they will be very close to an exponential decay in both cases. And with this exponential decay we can get the time scale of how fast this ring down is, and from that we can back out how much extra losses we have introduced into the cavity, and that is our absorption. So this is another kind of cavity enhanced spectroscopy. Now, I said that this one was very, very closely exponential decay, and this is actually a good way. This can also be used to calibrate photodetectors. So if we have a photodetector here we want to calibrate, we turn off a laser, we can do that very well, and then we know that this should be an exponential decay. So any deviation from an exponential decay, is because our photodetector is not linear. So this is used to calibrate photodetectors.